the next thing we're going to briefly talk about is what's called dimensional analysis. Sometimes it's very difficult to predict or model something using the fundamental equations, and so it's sometimes useful to be able to just see how things are related to each other in a more general sense. Now, we're going to start by looking at the governing equations, continuity, momentum, and energy, with an incompressible fluid that has constant viscosity within a gravity field. Now, you should work with the versions of the Navier-Stokes equations we defined in the last lecture when working problems, but this is just a simplified demonstration. Also note that we didn't derive the thermal energy equation in this class. That's actually left to the heat transfer course. However, I'm including it here just to demonstrate some of the concepts and ideas. This last term in the equation, this viscosity term, is related to what we call viscous dissipation, which is the conversion of mechanical energy into thermal energy through friction. Fluids heat up due to friction, just like solids do. And then C is the specific heat, so it's how much energy the fluid can absorb for a certain change in temperature. Now, we can actually define what we call dimensionless variables. So the dimensionless x-coordinate is the x-coordinate divided by some length scale. Now, we don't know what the length scale is yet. It's not really that important. We define that later. It's also important to note here that the x and v are vectors. X is the coordinates in 3 dimensions, x, y, and z, and v is the velocity in the u, v, and w sense. We have this dimensionless temperature, which is actually ratio of temperature differences to maintain a consistent variable system. Also, sometimes the reference pressure is 1/2 rho times velocity squared, or 1/2 rho v squared. It depends on the problem in question and what we're actually looking at. So we can make some substitutions and we can start to simplify. So when we do that for continuity, everything basically cancels out, and we don't have any more dimensionless products, what we call the dimensionless numbers. However, momentum does. We have a time scale. Over here we have a time scale. We also have a scale for the pressure. Again, if we used 1/2 rho v squared as our scale parameter, then P0 is 1/2 rho v squared, and we can get rid of this ratio. We also have a gravity scale, which scales gravity or gravitational forces to momentum, and we have a viscosity scale, a scale for the viscous forces. We also have some dimensionless products from energy. We still have this time scale here. We also have a thermal conduction scale. This basically scales the conduction and storage of thermal energy. And then we have a kinetic energy scale. So this scales the kinetic energy to the thermal energy for a system. Now, it's important to note that these are not the only dimensionless products that are important for fluid mechanics. If we consider compressible flows, we'll end up seeing Mach number and some additional dimensionless products. We can also look at boundary conditions and see dimensionless products that include surface tension or surface roughness and so on. The problem is that boundary conditions and so on are going to be specific to a particular problem. So we're not going to talk about them here. It's just important to be aware that additional dimensionless products exist relating these boundary conditions. Now, many fluids problems are too complex to come up with actual analytical solutions. There's so many variables to account for, and so on. Now, when we design experiments, it's usually best to change each individual parameter and observe how the result changes to come up with a model. That's not always practical. For instance, it's very difficult to find 2 different fluids that have the same density but different viscosity. So we want to think about ways we can simplify this, and one way we do this is the dimensionless terms, using dimensionless products. So we have this idea called the Buckingham pi theorem. The pi theorem describes the number of pi terms, or dimensionless terms. And to specify any problem, we need to have a number of dimensionless pi terms that's equal to the total number of variables minus the number of reference dimensions. Now, these dimensionless products, or pi terms, are things that are multiplied together that have no dimensions, similar to many of the circled terms on this slide. They have no dimensions. All the dimensions cancel out. Reference dimensions are usually base dimensions like mass, length, time, and temperature. Now, how we use the Buckingham-Pi theorem in practice, it's best to show by showing an example of a process. So the first idea is to list all the variables involved in the problem. So if we're looking at drag force, for example, of course we're going to have the drag force be one of the variables involved in our problem. We're also going to look at the velocity, the length scale or diameter of the object in question, the density of the fluid, and the viscosity of the fluid. So we have, say, 5 variables that we're going to look at when we're considering drag force on an object. And then we want to express each of those variables in terms of the basic dimensions, mass, length, time, and temperature. So for our example, we have force, which is kilogram meter per second squared, right? Newtons. So mass times length over time squared. Velocity is length per time. Diameter is a length, of course, and so on and so on. We can come up with the dimensions for each one of these. So then we use the Buckingham-Pi theorem. We have 5 variables here, and we have 3 reference dimensions, mass, length, and time. So 5 variables minus 3 reference dimensions means we're going to need 2 dimensionless terms, or pi terms. So then we need to select our repeating variables. So the number of repeating variables is equal to the number of reference dimensions. And in fact, it's usually a good idea to have your repeating variables represent those dimensions. So for instance, diameter only has dimensions of length, so it's a good representation for the length scale for the problem. Density is a good measure of mass. So we typically use density to represent mass. And you can also use velocity to then represent time. As in combination with diameter, velocity will give you a time scale. So a lot of the times you'll see repeating variables of density, velocity, and diameter, or some other length scale. Now, there's nothing preventing you from using viscosity, in this case, as a reference dimension. It's just not convenient for this type of problem. It's also not usually a good idea to select the variable of interest as one of your reference repeating variables. For instance, if we're interested in finding the drag force, we don't want to use drag force as one of our repeating variables, because then it'll show up in every single term, and we want to avoid that if possible. So the next step is to form our dimensionless pi terms. So the way we do this is we set up an equation. We set up that pi 1, the first pi term, is equal to density to some power times velocity to some power times diameter to some power times our force. And we want this to be dimensionless, right? So we want the dimensions of all of these multiplications to add up to no dimensions. So we start by creating an equation for the dimensions of the pi term. So the dimensions of density to the a times the dimensions of velocity to the b times the dimensions of diameter to the c times the dimensions of force should be equal to mass to the 0, length to the 0, times time to the 0, power. And now we can divide this up into 3 separate equations. We divide this up into an equation for mass, an equation for length, and an equation for time. So we can actually solve these equations. So for instance, if a plus 1 is equal to 0, then we know that a is negative 1. And if negative b minus 2 is equal to 0, we move b over, and we can see that b is 2, negative 2. So here a is negative 1, b is negative 2. And if a is negative 1 and b is negative 2, we can use this equation to find that c is negative 1. So then our pi term, pi 1, is going to be equal to f over rho v squared times diameter squared. C should be negative 2. So then we need to verify that the dimensions cancel out. So we check the dimensions of each term, and we make sure that all of the different terms are dimensionless.